Welcome to another lecture for interactive computer graphics. All right, so today's lecture is going to be a little bit different than our previous lectures. So the stuff that I'm going to talk about from now on is going to be advanced topics related to interactive computer graphics. So we learned the basics and how to use the GPU up until today. Moving forward, we're going to look at some advanced techniques of interesting things to do with all the stuff that's available for us on the GPU. That's going to be our main topic for the rest of this course. And I'm going to be talking about some advanced topics in every lecture. They're going to be related stuff. And I'm planning to talk about them at a relatively high level. Today, it's going to be a little lower level because today, the stuff that we're going to be talking about is very closely related to the upcoming project. That's why I'm talking about that topic now instead of some other advanced topics. So the stuff that I'm going to be talking about today is actually going to be stuff that you guys will be implementing as a part of the last project before the final project. Not all of it, but a part of it. All right. So let's go ahead and jump in. Our topic for today is going to be this whole stuff: bump mapping, normal mapping, displacement mapping, and parallax mapping. They are all related stuff, and we'll go all over them. So that's our topic for today. Let's start with the simplest one, the earliest one. That's bump mapping. It's a very, very old technique, actually. Bump mapping. It's been around for so long in computer graphics. The idea is that we would like to be able to add some geometric detail to our objects without actually adding the geometric detail. So we would like to get the appearance of this small scale geometric detail without generating so many vertices and rendering all of them, because that would be expensive, right? So you imagine all these small little dots in here, right? Small little bumps and dents. If I were to generate a high resolution enough sphere to represent this, to model this, that would be a very, very high resolution sphere. That would be very expensive to render. But a simpler sphere like this one, it's so much easier to render. It could have lower tessellation levels, right? And the way I achieve this look by rendering this object is by adding this bump map in the middle. Right? So this bump map is going to define the bumps and dents on the surface. And the idea is actually fairly simple. So let's talk about that. Now, I have this, let's say that I have this flat surface, right? It's totally flat. That means all of my surface normals are pointing up, right? Now, this, obviously, I shaded properly, and this is going to look like a flat surface. But if I fiddle with the normals, if I change these normals and make them look like this, now this is still the same flat surface, but because of shading, this has the normals of a surface that looks more like this, right? It's not that surface, it's still flat, but it kind of its normals are coming from a surface that looks more like this. So when I render this flat surface with these normals, it's going to look more like this to me, even though it's not. It's actually this with just the wrong normals on it, right? So that's the idea. That's a trick. So instead of changing the geometry, we are just changing the normals so that the geometry does not look quite like this, but shaded image gives me the appearance of this surface in the end. And the way we do this is using bump maps would be by defining the height or the bumps on the surface or the dents, right? And the way we define it would be just using some colors, a color map like this. So this is what would be a bump map. So here, dark means lower and white means higher, right? So you see that there's this gradient going from dark to bright, so black to white. That means I have a ramp, right? And then another ramp down and then a ramp up, down. So this is what this bump map specifies. So sometimes we call this a height map because it sort of specifies the height of the surface at any point. So the value here between 0 and 1, 0 meaning black and 1 meaning white, that tells you the height of the surface at any point, right? It's a very, very simple idea, but by using this height map or bump map, we can generate the appearance of a surface like this. And when we apply it on a surface, you sort of get the appearance of it. So this one is an actually tessellated high-resolution model that is deformed using the same height map or the bump map. And this one is just using bump mapping. And as you can see, if you look at the silhouette, if you look at the edges, you will see that this one has some wrinkles around the edges. This one is perfectly smooth around the edges, like it's a perfect sphere. It really is. But it doesn't quite look like a perfect sphere because the surface normals are sort of modified when I'm shading. So it has the appearance of this high resolution model, even though it's actually a smooth sphere, right? So that's the idea with bump mapping, and it's used a lot actually for all sorts of things. So here's an example showing some wood texture applied on a sphere. Of course, yeah, spheres, yeah, we typically use them for simpler shapes like flats. There's a box here, but I apply some bump mapping on it. So if you look at it, this one looks really detailed, right? It's as if there's quite a lot of geometric detail on it, but this is the one that we're actually rendering with just an additional bump map. You get a lot more detail in here, and it looks like a much higher resolution model than it actually is. Here's another example. You see that the same model, we just applied some bump mapping on it, and you see all these bumps and dents on the surface. Just gives you a lot more geometric detail, the appearance of a lot more geometric detail, even though there isn't any more geometric detail. This is still a flat surface, right? And we're getting these geometric detail by just modifying the surface normals. Now the way this works is that with bump mapping, as I said, it's a very, very old technique. I need to figure out the surface normal of this ramp, right? So I have a gradient of color going from black to white here, and I need to figure out the surface normal of this. The way that we're going to do this is not like, I'm not going to try to place a surface or anything, but what I'm going to do is that at any point here, I am going to look at the gradient. I'm going to look at how the height map value is changing in that neighborhood. So you look at the neighboring pixels. By comparing the colors of neighboring pixels, you can figure out, oh, this color is the value here is increasing in this direction. Of course, you can do that in 2D, and based on that increase, you take the surface normal and you perturb it. You just perturb it along some direction. Of course, you can adjust the magnitude of that. If you crank it up, it's going to look like this height map is going to be like exaggerated a little bit. So you can sort of adjust how much you're deforming. Yeah, so that's the general idea. You look at the neighboring pixel values for the bump map, and based on that, you perturb your surface normal. Very, very simple, but it's a little bit annoying in the sense that you kind of need to look at the change of the height map values here when you're using bump mapping. You need to look at the gradient. You need to look at the value differences. It's okay, it's not that hard, but I just need to look at the neighboring pixels and then compute the differences, and that's how I do it. It's a little expensive, just a little bit, because if you're going to do that on the GPU in the, let's say, fragment shader, for you can't just read a value from the bump map and say, oh, height value is this, so my surface normal. Like, the height value alone is not enough. You need to know how the height is changing. So just reading one value from the texture map for the bump map is not going to be good enough. You're going to have to read multiple values. You're going to read a value that's a little in one direction, a little in the other direction, and you need to figure out how the height value is changing, and based on that, you modify the surface normal. That's the annoying part of bump mapping. As I said, it's an old technique, but that's how it works. It works well, but it requires these additional texture reads and stuff. Wouldn't it be nicer? Wouldn't it be nicer if I pre-compute these normals and just store these normals directly, right? Instead of storing these heights, I store the normals, because what I need is the normal, right? I don't care about the height. I'm just using that height to find the normal. So wouldn't it be much nicer if I were to just record the normals, and that would be normal mapping. So this is a relatively newer technique, but it's a very obvious next step from bump mapping, right? So let's say that I define my normals based on some height map, just like bump map, but instead of perturbing the normals at runtime by looking at how the height value is changing in the bump map, I pre-compute them and record them. And so in this case, I have two types of normals, right? Normals in this direction, normals in that direction. So I have two colors. So one color represents normals in that direction, the other color represents normals in that direction. So based on these colors, I can tell exactly what this normal is supposed to be. So I can read any point on this normal map, and that normal map gives me the surface normal, right? It's a lot easier that way. And the way that it works is that, well, it's going to be like, how do I calculate these colors, right? How do I convert a color value to a normal vector, or do the opposite? When I have a normal vector that I want, how do I encode it and put it in a normal map? It's not actually too hard. It's here's how we do it. The thing is, the normal vector will be in this space, right? It's going to be a vector. It's a unit size vector. So any normal value will be in this space. Actually, it's going to be a little more limited than this. Normal values will be normalized vectors, so their length will be 1, right? So they will actually be on a sphere. So all these normal values will be on a sphere contained inside this cube, right? From -1 to 1. And we convert them to color values. So the color values will range from 0 to 1. So you just take your normal value, whatever that is, that's going to be on a sphere, and you map it onto a color value here. Again, it's going to be on a sphere inside this volume, right? Inside this RGB color space. It's going to be on a sphere, right? So Z coordinates would be represented by blue, X coordinates will be red, and Y coordinate will be green, obviously, right? So very, very simple mapping. And from a given normal value, you can compute its corresponding color value. From given normal color value, you can compute its normal vector fairly easily, right? Now, the thing is that we may want to, when you have a model that's normal mapped, we may want to animate that model. So you can apply in some normal maps on a character, for example, and the character is moving around. So that the surface of that model is deforming. So as the surface is moving around, I'm going to represent these small scale, tiny little details with the normal map, right? I would like those tiny small scale details to move around with the surface. That's what I would like. So this normal map, this X, Y, and Z coordinates will be defined on a local space. So it's not going to be in object space, but it's going to be on the local space of a point on the surface. So here's what I mean. We're going to define these X, Y, and Z coordinates based on the point on the surface. So the Z coordinate is typically aligned with the surface normal, the actual geometric surface normal, before we modify the normals with normal mapping. So Z coordinate will be aligned with that. And for x and y coordinates, we typically compute them from the texture mapping, the UV mapping. So this will be in the direction of u, this will be in the direction of v, and this will be in the surface normal direction. So you get a coordinate frame like this. So given this coordinate frame, you can take any normal map color value, RGB color value, map it into XYZ for this coordinate, and then from this coordinate, you can transform it to whatever coordinate you will need. Right? So that's the idea. Now, because this geometric surface normal is aligned with the z direction, normal maps will have a lot of blue in them, because we use normal maps for perturbing the normal slightly, typically. So for a lot of the surface, I'm going to have normal values that will be close to the geometric normal, and the geometric normal will give me blue, right? So oftentimes when you look at a normal map, it will look like something like this. There's going to be a lot of blue in it because of that. So there's going to be, when you see red, that means you're perturbing towards the x direction. When you see green, means you're perturbing towards the y direction. When you see, but this is, as you can see, the average color here, the blue is not perfect blue. It's actually blue with some red and some green in it. So it's like mid-range, some 0.5 red, 0.5 green, and 100% blue. That's what the average color is. If you have less red, that means it's x direction in the opposite x direction, right? If you have less than 0.5 red, that means you perturb in the negative x direction, right? So here's what I mean. Like, I can just put it on here. You can see that this is how this normal map fits in this normal, tangent, and bitangent directions, x and y, right? All right, so if you have a flat plane like this normal mapping becomes much easier, because the x, y, and z coordinates of your flat plane will just correspond to the same coordinates in the normal map. So this transformation that I was talking about from this local tangent space to object space, and then to camera space, to whatever, that simplifies quite a bit, right? So that if your object is totally flat and is not deforming, like a flat plane like this, then basically you can treat your normal maps as if those normals are defined in object coordinate frame, right? Because they're going to be the same. But of course, if I take this plane and start deforming it, things are going to be a little bit different. All right. So let's see what this looks like. This particular normal map gives me a pretty nice looking brick texture, right? With all these details. Right, so it's actually very difficult to look at this and say, oh, this is just a flat plane with some normals modified. It actually looks like the real thing, right? It actually looks like all these tiny little details are modeled, but they're not. There's not enough geometric detail here. It's just a flat plane. So that's the idea. This makes it really cheap. So here's an exaggerated view of a normal map. So this is the actual geometry where this normal map is generated from. So from this geometry, I can generate this normal map, right, by looking at the surface normals at any point, and I can apply that normal map to a surface, a flat surface. Well, of course, if your surface is, if you're not representing just small scale details, but like these giant shapes, when you start looking at it from an angle like this, it doesn't quite look right anymore, right? It's just, yeah, you can tell that this is sort of flat somehow, although it looks a little weird because the normals are not quite right, but it doesn't, the illusion sort of breaks. So the normal maps work when they are representing small scale details, but for giant deformations like this, they're not going to work out so well. So here's an animation showing this. So from the top view, kind of looks okay. I mean, you don't get the shadows or anything, but other than that, the shading looks okay from top view. But as you tilt it, it kind of loses its ability to represent these really exaggerated geometric details. So over here, this is the normal map part. This is the actual geometry part. The actual geometry looks fine. The normal mapped part, so the illusion breaks when you rotate it. And it breaks because these are really giant deformations on the surface. If you were talking about minor modifications of the surface, normal maps would be just fine. So here's another example showing normal maps on this flat plane. When you look at it, it's like, wow, like those details are actually in there as if, but they aren't, right? So it actually works pretty well if you use it right. If you use it for defining these small scale details, it actually works really well. And it's very, very useful, right? So if you want to model oranges, for example, something like this, you really don't want to model these small scale details. It's very, very hard to do. But it's much easier to just paint it on a texture with some bumps and dents and then convert it to a normal map and apply the normal map, and you get this really nice looking small scale details on the surface. Right? So this is used for offline rendering, not just for interactive rendering. It's used for interactive rendering, also for offline rendering too, because this is so much easier to model than the actual geometric details of this orange. And if I'm not going to zoom in and see these tiny little bumps and dents on these oranges, then who cares? For real-time rendering in games, we can even exaggerate them a little bit, and they work just fine. So you can see the underlying geometric detail here, just with the triangles, and with the normal maps applied to this surface, it's as if these objects have a lot more geometric detail, but they don't. But it just works fine, right? You look at it, but pay attention to the details. Like these larger details are actually modeled. You use normal maps for small scale details, not for giant stuff. Yeah. So in the end, you get something that looks as if it's really highly detailed and expensive, but you're using a very cheap model for rendering it. It's not just about rendering. Yeah, you have some savings in rendering. It's faster to render with normal maps, with this lower resolution model with normal maps, than it would be to render the high resolution model. At the same time, this might be easier to model too. So from a content creation perspective, you can just get a texture like this, open up in your favorite texture editing software, let's say Photoshop, and you draw these lines and convert them to normal maps, and then you're done, right? It might be, I'm not saying it always is, but it might be even easier to model. But it's definitely faster to render. So if you were to compare normal maps and bump maps, you'll see that this is the bump map and this is the corresponding normal map. They're sort of interchangeable, right? So you can sort of take any bump map and convert it to normal map. You could take a normal map, convert it to a bump map, but they are sort of different representations, and they don't match each other perfectly always. And the reason for that is more related to how bump maps are used at runtime for computing the perturbation of normals. In theory, if you use the same procedure, if you start with a bump map that defines a height map and use the same procedure that you would use for rendering the bump maps, use the same procedure for generating a normal map, you won't be able to tell the difference between a normal map and a bump map when you're rendering. You'll look at them, they will look exactly the same, right? You could be using this bump map and use bump mapping, or you could be using this normal map and use normal mapping. You will get exactly the same result if they actually match each other. That the parameters and everything should match each other. So the parameters you use for how much you perturb using the bump map, and parameters you use for converting this bump map into a normal map, if they are the same, then the final result should look the same. But in practice, there are always some minor differences. So if you Google it, I'm pretty sure you'll find all sorts of examples comparing bump maps and normal maps, and they will look different because people are not necessarily using exactly the same parameters for normal maps and bump maps. So they might look a little bit different. But the nice thing is that with bump maps, you are representing the height map, and then you convert that height map to normals at runtime. And that's going to be a little bit clumsy. With normal maps, you're directly recording the normals. So you have more freedom in how you define the surface normals using normal maps. So these bump maps, the surface normal is defined by the variation of the heights in the neighborhood, right? With a normal map, I just specify whatever normal value I want. So I can pick and assign whatever normal value I want. I have less of a flexibility when it comes to bump maps. So given a normal map, you may not be able to convert it to a bump map that would exactly reproduce the same results. This is covering a portion of the possible space, possible normals. So bump maps will not be able to represent everything that normal maps can represent. So that's why you will see a lot more detail with normal maps. So bump mapping is the old technique. Normal mapping is the modernized version of this old technique, which is a little bit more powerful. But for both of them, we're actually not modifying the geometry at all. We're just rendering the same old low-resolution geometry. All we're modifying is the surface normal we use for shading. That's it. And that gives us the appearance of this high-resolution model, even though there is no high-resolution model, right? But what if I wanted to get the high-resolution details? Like, these will break if I look at them from grazing angles. If I zoom in and look at the surfaces close enough, these will really break. This illusion works from certain distances, from certain angles, but from some angles, this is not really going to hold, especially if the deformation, the height variation is large enough. This is not going to hold. So if I want to actually get the geometric detail, the method that I can use is what's called displacement mapping. The idea with displacement mapping is, again, use some sort of a texture map, but actually generate the geometric deformation. Geometric deformation. So I'm not going to be rendering a flat surface like this, but I will be rendering a deformed surface like this instead, using displacement mapping. That's the idea. So that means that I'm going to have vertices here. If I'm going to have a high-resolution model like this, I'm actually going to have a high-resolution model like this, right? So I'm going to have these vertices, and I can start with a flat surface where all my vertices are on this flat surface, and I am going to modify the positions of these vertices using a map like this. That's going to be my displacement map. So again, I'm going back to the height map. So this is, again, a height map. This height map defines how far I need to move these vertices along the geometric normal of the original surface. So I move them along, move them up, right? And based on these height map, displacement map values, I'm displacing them. Now, the concept of displacement mapping is a little more general than just height maps, because instead of just storing an intensity value from 0 to 1, I could be actually storing colors, RGB colors, right? So I could be specifying deformations not just along the surface normal, but I could be specifying deformations in the tangent and binormal directions, right? So I could have an RGB color that defines that perturbation. So displacement map can represent a 3D perturbation, but typically, oftentimes we just use a height map like this, because this is, for a lot of applications, this is more than good enough. If you have these perturbations along the surface normal, it's oftentimes more than good enough. And that would be a little bit easier to handle because I'm just modifying the vertex position along the surface normal. Presumably, I already know the geometric surface normal of the original surface that I'm rendering at any point. So I just move things along that direction based on what I see in the displacement map. So there is no faking here. This works just fine because I'm actually modifying the surface. I'm actually getting a high resolution surface. Like here's an example. I can get a highly tessellated model like this. It's a flat surface. I apply this displacement map, and in the end, I get this displaced surface. And it's actually displaced. It has this geometric detail to the resolution that I can represent. So in the end, this is going to be, yes, a lot more expensive than normal mapping or bump mapping, but I'm going to have the actual geometry here. So there's nothing fake, right? This is the actual geometry. It will work just fine. And it's not going to break. I can have really strong deformations on the surface, and that's fine. That's totally fine. I'm actually modeling this, right? So displacement mapping works perfectly fine, and that's why it's a very common tool used in offline rendering. But in offline rendering, oftentimes we use displacement mapping for representing small scale details, because if you have large scale details, you can just model them using polygons. But with small scale details, it becomes really cumbersome to model them by hand, by moving every vertex in the surface normal direction a little bit. I mean, we can use software like ZBrush, for example, that sort of allows you to paint on the surface that is automatically converted to deformations on the surface. And you can record them as this high resolution surface in the end as your output, or you can have a relatively low resolution surface with a displacement map applied on it. Now, why would I want to do that? Because then I don't have to store this high resolution model, but instead I'm storing the low resolution geometric model with a displacement map that I can use at render time for adding this geometric detail. And how do I do that? Any guesses? Starting with a low resolution surface, how can I possibly get a higher resolution surface? We did something similar to that last time. We talked about this. Tessellation, right? So I can do tessellation. I can start with a low resolution model, tessellate it when I'm rendering, and then I can apply displacement maps on top. That would give me the small scale or deformations. So let's compare these methods again. So this is bump mapping. So it's just a box. I apply some bump map on it. You get these nice looking details. Looks pretty nice if you ask me. Much more exciting than just a flat box surface. And there's no diffuse texture here, right? It's the same diffuse color. It's just the shading differences appear because I'm using a different surface normal, because I'm perturbing the surface normal using this bump map. I can do the same thing using normal maps. Here's the corresponding normal map. Same thing, but it seems like these normal differences are a bit more exaggerated. And that's related to what I was telling you earlier. This might be the normal map might be corresponding to this particular height map, but I can represent normals a bit more freely using normal maps, so I can actually specify these details and with a bit more detail using normal maps. So oftentimes you will be able to get much nicer looking results using normal maps because of that. But again, this is just flat, right? There's no surface deformation. It's just I'm just modifying the surface normal that I'm using for shading. So if you look at this face, the top face, the illusion is still sort of there because the deformation is not too much, but you can tell by looking at the edges, it's actually flat, right? It's not really deformed that much. But I think in this example, the illusion still holds because I'm not modifying the surface by much. But if I were to modify the surface properly, then I could just use displacement maps, Normal mapping with displacement mapping, it will look like this, right? With displacement mapping, I'm actually modifying the surface. So normal maps, displacement maps would give me the actually modified surface. But of course, I have a lot more geometric detail here. So I will be rendering a lot more triangles to be able to get this. And you may notice that this is really super highly tessellated box, and still maybe the geometric detail is not quite high enough to represent some of these small scale details. It's there, I think, but it's you're gonna have some limits in terms of the geometric detail you can handle, or at least beyond some point it's going to be really, really expensive because I'm actually generating this geometry. Now, this discussion of normal mapping and displacement mapping is a little misleading, so I'm going to fix that part right now. Displacement mapping, just modifying these vertex positions, is not enough. Let me say it again. Just modifying the vertex positions is not enough to produce this image. If you just modify the vertex positions, you will not see any of these surface details. Even though the geometric detail will be there, but in addition to modifying the vertex positions, you also need the modified surface normals, right? Just moving the vertices around, yeah, you're modifying the geometry, but now I need to know the modified surface normal. Without the modified surface normal, I won't be able to render this high resolution surface properly. So displacement maps almost never used on their own. I mean, it could be used sometimes, but typically, most of the time, we're going to have a displacement map with an accompanying normal map with it, right? So I'm going to have displacement mapping plus normal mapping to be able to get an image that looks like this. So this is not just displacement mapping, this displacement mapping and normal mapping. Now, let me clarify one point here. You can definitely use displacement maps on their own. But if you're going to do that, you need to apply the displacement maps before rendering. You need to generate this high resolution model, apply the displacement map, compute the surface normals, and then you can render them. Yes, you can definitely do that. If you're going to apply the displacement map on the fly as you're rendering, well, then you'll need to compute the normal perturbation by looking at the variation in the displacement map. You'll look at the displacement map is a height map, so I can also use it as a bump map, right? So I can look at the displacement map to compute the displacement. At the same time, I can look at the neighboring pixel values in the displacement map to compute the variation of the height map. And from that, I can treat it as like a bump map and try to compute the surface normal at runtime, and I can do that. Or much easier, I can just generate a normal map that would go along with my displacement map and be done with it. So this is the typical use case. Most of the time, displacement maps will have a corresponding normal map because that makes the implementation so much easier and rendering becomes cheaper. But just to clarify that it's not a requirement. Technically, you can just use displacement maps as long as you're okay with computing the surface normals on the fly as you need them. Right. But you will get better detail with normal maps. The reason for that is the geometric detail you can get with displacement maps will depend on your actual geometric detail with your tessellation. It's going to be limited by that. I can have a super high resolution displacement map, but if I don't have enough vertices to displace, then I'm not going to get a lot geometric detail out of my displacement map. So the geometric detail I can get is limited by the geometric detail I actually have, right? Not just by the resolution of the displacement map. The same is not true for normal maps though. If I have a super high resolution normal map, I'm going to have super high resolution details on the surface, right? Because I am modifying the surface normal at every pixel sort of independently, sort of independent from the geometric detail. All right, so this is displacement maps, and the problem there is that it will require you to actually generate these vertices, and there's some cost associated with them because you're actually rendering a super high resolution surface now. And that's not always nice, because sometimes with displacement mapping, yeah, I'm generating all these vertices, but sometimes the geometric detail that I want is so high that it's not going to be sufficient to just generate these vertices. Sometimes it's going to be super hard to have, or super expensive to generate enough number of vertices to represent the detail that I have on my displacement map that I actually want. So what can I do in that case? So what I want is that I want to be able to render this model, right? This modified surface. That's what I want to be able to render. But I don't want to pay the cost of actually rasterizing all of these vertices and all the triangles that come out of this highly tessellated model. So I would like to get the illusion of this, right? I would like to get not just the illusion, I would like to get the appearance, the exact appearance of this displaced surface, but I would like to render this flat model. Can I do that? Actually, there's a way to do it. So imagine that instead of extending them up, I do the opposite. I put my surface up here, and my depth map just represents dents into that surface. Similar thing, right? So I can actually do this. I can actually get this full geometric detail of this displaced surface without having to render that displaced surface directly. And here's how I do it. Say that I'm rendering this is my camera, and for any pixel or any ray that corresponds to that pixel, like this is the surface point that I see for this particular view direction and on my camera, which corresponds to a pixel, right? So if I were to render this low resolution model, this is what I would see. This is what I would get in my fragment shader. Inside my fragment shader, I can actually do some sort of ray tracing. It's not exactly the same kind of ray tracing, but I can go deep into this volume underneath the surface, and continue tracing that view direction until I find the intersection with the surface that I actually want to shade, that I actually want to render. And then I can use the position and the UV coordinates and the surface normal of this position instead of this position, right? I use this green point, I shade this green point, I compute my shading at this green point instead of this blue point, and that will give me the exact appearance of this high resolution model, of this displaced model, without paying the cost of actually rendering it. Of course, this is not super cheap, right? I need to figure out a way to go from this point all the way to that point, so that's going to be sort of expensive. I'm going to have to go on this displacement map. I'm going to have to figure out where I find this intersection, and that's going to be expensive, but it is doable. It is definitely doable. Using something like ray marching is possible, so you can think about this as like volume tracing. There are other ways to handle that as well. If you want to learn more about how to do this, I would suggest that you check out per pixel displacement mapping. This is used for offline rendering as well. So you apply a displacement map, and then you can zoom in into a model as far deep as you want, and you're going to get all the geometric detail that you have in your displacement map to the resolution of your displacement map, not to the resolution of the actual model that you're rendering. But we can do this on the GPU as well in the fragment shader with interactive rendering. Check out per pixel displacement. That's the idea. Of course, this is going to be a bit more expensive, quite a bit more expensive, right? You kind of need to figure out what you would see if you were to actually render this displaced surface. All right, so that's the idea. Now, instead of doing this though, sort of per pixel displacement. A more popular technique that's used in interactive computer graphics is what we call parallax mapping. It's a similar idea. It's an idea of approximating this very thing. It's approximating the displacement maps and actually properly using the displacement maps without generating the geometric detail. Right? Doing this per pixel displacement, but not paying the full cost of doing per pixel displacement. So this is going to approximate per pixel displacement. That's what parallax mapping does. So let's say that I'm looking at the surface from this side. So this is the point that I'm seeing, and I would like to get this blue point here. This is the point that I would like to shade, but finding that can be expensive. So to make this cheap, here's what parallax mapping would do. In parallax mapping, I'm going to look at this point. I find the UV coordinates of this point. I already have that in my fragment shader. And I'm going to read my displacement map, and it will tell me how far deep the surface is at this point. Right? If I know the UV coordinates of this point, which I do when I'm doing in my fragment shader, I know that. So using that UV coordinate, I can just look up that texture and it tells me how far the surface is from that point. Now, what I do with parallax mapping is that I'm going to take this length, and I'm going to say, you know what, I'm going to use this length to continue along this view direction with the same length, and I end up at a point over here. And I'm going to assume, okay, this is the point where I actually find the surface. Now, this is, of course, not this point that I want, but it's sort of a like rough approximation. It's a very approximate way of guessing what point that I would see. But it's very cheap, so that's the advantage of it. So here, I'm just using this length that I read from my displacement map, and I use that length to continue traveling along this distance. I find this point, and I say this is, I'm going to assume that this is where I hit this displaced surface. And over here I have a different UV coordinate, right? That corresponds to this point on the surface. I have a different UV coordinate, and I can render this object using that different UV coordinate over there. So as you can see, it's not exact, it's approximate, but it actually works pretty well. So here's parallax mapping in comparison to normal mapping. If you pay attention to this, even at around the edges, you'll see a lot more detail than you would get with normal mapping. So because this is not just modifying the surface normal, this is actually sort of approximating that displaced surface. It's not exactly computing that displaced surface, but it's approximating that displaced surface. Now, this approximation is actually pretty good and okay if you're looking at the surface head on like this. But if you start to rotate this surface, it's not going to look that great. I mean, it still looks like something like, you know, it's not just normal mapping, right? You can see that, oh, there's some surface detail, but it looks a little weird around the edges here, right? So it's like the details are not quite right. Over here in this example, some of the details are distorted a little bit, and that's all related to that inaccuracy that you have in finding that actual point that corresponds to your view direction. So you don't find the correct point on the displaced surface. You have an approximation of that, and that approximation is oftentimes bright when you're looking at the surface from grazing angles. Or if you're looking at it head on, it works much better than when you're looking at it from some angle like this, right? So what do we do? How can we possibly fix this? We can actually improve on this a little bit. If you're okay with doing a little more expensive parallax mapping, we can do what's called steep parallax mapping. So with this steep parallax mapping, the idea is that I'm going to split this total depth that I have in my displacement into multiple pieces, as many steps as I want. And with steep parallax mapping, I'm going to do exactly parallax mapping, but I'm going to limit how far I am allowed to go from one point to the next. So in the first step, I read the depth value here, and that tells me, oh, I need to go this far into my surface. But I'm not going to go all the way here. I'm going to go up to the next step. Right? This is where I have to stop. This tells me I need to go really far, but no, I'm not going to go all the way. I'm going to stop here, and I'm going to read the displacement map, the height map at this point as well. At this point, I read the displacement map. It gives me, whoa, I need to go a lot. All right, I'm going to go a lot again, but no, I'm going to go all the way to the next step only, right? And I'm going to stop over here. Now I read this one. It says, oh, I need to go even further. And again, I'm going to stop at the next level. I'm not going to go any further. And at this level, I realized, oh, actually, I went a little too far. The surface was up here. Okay, I can stop there. All right, so I went far enough. So I stopped there. So this is steep parallax mapping. It's just go step by step. And with steep parallax mapping, I get a better approximation of the surface. But it is more expensive, right? So instead of doing just one texture read at this point, I ended up doing multiple texture reads. So up to however many steps I have in my height map here. So in every step, I am changing my UV coordinates accordingly, and I'm reading a different position on the displacement map. So based on that, I decide how far I need to go. So this is going to be more expensive because it's doing multiple texture reads and multiple dependent texture reads too. It's like I read the texture value, I compute a new UV coordinate, and then I read the texture based on that modified UV coordinate. So it's considerably more expensive than parallax mapping, but you get better results. So in a lot of cases, it's actually worth it. So with steep parallax mapping, you can still see some steps here if you pay attention. It's not perfect. There's some steps, but it actually works okay. Even from this angle, I think it's just fine. Of course, if you exaggerate it quite a bit, it's not going to work as well. In this case, you are actually seeing the individual steps, right? At some point, it starts showing it's not that perfect, right? But we can do better. We can do better, and it's not that much more expensive. So instead of using steep parallax mapping, we can use what's called parallax occlusion mapping. The idea is very similar, but we add one more step. So we do steep parallax mapping. With parallax occlusion mapping, we start with steep parallax mapping. We go next level, next level, next level, and then when you realize, oh, I went too far. Okay, at this point, can you see, at this point, I have a surface, the correct surface position was up there. Well, at this point, the correct surface position was up here. I know those. I just don't know what's in between. So what I'm going to do is that I'm going to assume that this part is flat, but it's flat. If it was flat, I have this correct surface point and that correct surface point. I can approximate the hit point in between, the intersection in between, by treating this as a flat surface in between. So it's not that much more expensive. It's just a little more compute. You add no more additional texture reads, just a little more compute. You find the intersection with this plane, and you use that point as your approximation. And as you can see, it's a much closer approximation, right? It's not over there. It's not over here. It's very close to the surface. So in that sense, it's much closer. But more importantly, this is going to give me a sort of closed surface, right? Even if this is not a perfect approximation of my displacement map, it's still giving me a ramp in between these steps. So you sort of smooth over these individual steps nicely. So when you render parallax occlusion mapping from grazing angles, it looks just fine, right? It doesn't have any of those problems anymore. and you can look at it from great grazing angles, and it works just fine. It's as if the geometric detail is in there. So this is an approximation of per pixel displacement mapping. It's a little bit faster, but the idea is very, very similar, actually. You can even think about parallax occlusion mapping is a way of implementing per pixel displacement mapping. It's slightly approximate. So here are some parallax mapping examples from actual games. So over here, can you see where parallax mapping is applied? That's a large scene, right? There are lots of things going on. Parallax mapping could be anywhere. The trees could be the trees, but no, it's actually right. The parallax mapping is on the stairs right here. So the stairs here, it's just that one flat surface. But when you look at it, it does not look like a flat surface. Actually, in 3D with motion, it would not look like a flat surface at all because we're using parallax occlusion mapping, right? So you actually have that surface detail, even if you're not actually rendering that surface detail. Here's another example from a different game. Here, I think it's sort of obvious where the parallax mapping is in this case. It's just all the walls and the bricks. As you can see, have this high resolution 3D detail, and it's coming from parallax mapping. Here's another example from Crysis. In this case, you can see all this geometric detail without actually having to render all that geometric detail. With parallax mapping, we can get that. Another one. So this, I believe, is steep parallax mapping, but it works really well. You can still see a lot of geometric detail. The illusion, however, breaks along this edge where the two ends of the walls, the two walls come together along this edge. You see that it looks like a very perfect edge, right? Yeah, so it doesn't have to break. If you are super careful, you might be able to figure out ways to make sure that they connects well together with parallax occlusion mapping. You can actually handle that in theory at least, but in practice it's not that easy to handle those details. So it's not uncommon to get artifacts like this where the illusion sort of breaks. Right. Let me show you another example. I really like this one. This is well, it's a flat cube. It's nothing interesting here, but if I apply parallax mapping here, I can make it look like this, right? So it's really super deep crevices here, and you can see those. Here's another visualization just showing some grid lines over it, so you can see the details, the 3D details very nicely. All right, let me show you a video. All right, so in this video, you can see that there's just some texture on the floor. It's all flat, nothing is happening. And now the user is going to apply some shadows, and he's going to apply parallax occlusion mapping. You ready? As soon as parallax occlusion mapping comes in, you start seeing this surface detail, which actually, you're just still rendering that flat surface, but that's not what you're getting, right? And you can use that for computing shadows as well. So all your shadow maps and everything could be using parallax occlusion mapping too. So you can have proper shadows. So all these this detailed surface can be casting proper shadows onto itself. But I believe in this case the shadow of that object on top of the plane is not quite right, but there are ways to fix that as well. Is that right? I'm having difficulty seeing it from this distance. Yeah, but you can actually get that right as well, because with parallax occlusion mapping, you're actually computing the 3D surface. Right. So anyhow, that's an example. Here's a demo that you can play with as a WebGL demo. Actually, you know what? I'm gonna show you this demo. I really like this one. It's a cube using this displacement map and this normal map applied on it. Let's see. Does that work? Oh, there it is. Okay. Let's start rotating this. So this is showing different methods. So if we don't have anything, it's a flat surface, right? Nothing is happening. Now I apply normal mapping. Okay, over here it looks okay, but up there, not really, right? It's the illusion sort of breaks up there. Not so great. And also, as the cube is rotating, the illusion starts breaking. With parallax mapping, you get better results. And now, how far we want to extend the depth? Let's say we're going all the way. And as you can see over here, like as it's rotating, you start to get some artifacts, right? The surface separates, and up here, things are really messy, right? It just doesn't work out so well. But I can add steps with steep parallax mapping. So this is adding a lot of steps. Let's use just a few steps here. Just 1 step, 2, 3. Yeah, you can see you can see multiple steps, right? Up here you can see multiple steps, and on the sides you can see multiple steps as it's rotating. But as I increase the number of steps, it starts working out fine. Still up here, you should be able to see some separate steps, right? But yeah, if you really crank it up all the way to 32 here, it works okay. But let's keep it relatively low. Over here, I think this is okay. And let's switch to parallax occlusion mapping. So steep parallax mapping and parallax occlusion mapping. So you see, all of a sudden it just fixes all of these gaps between levels. And of course, if you are not using enough levels, it will still have some inaccuracies, right? It's still trying to approximate that surface. If you use enough number of steps, though, it does a pretty good job. As you increase the number of steps, you reduce the error, and even from grazing angles, it starts looking so much better. Right. All right, enough of spinning bugs. Let me show you what we're going to have next as a part of our project. So in our upcoming project, we will be implementing normal maps and displacement maps using tessellation shaders and geometry shaders. Now, I did a demo last time and I showed you what it was producing. So this is going to be a little bit of an easy example for normal mapping, because normal maps here, you can treat them as if the normal maps are defined in object space, because we're not going to deform the underlying surface here. Surface is going to be just flat, plain. So you can treat this as if they are object space normals. Right? So normal mapping becomes quite a bit simpler with that. And that's what we're going to implement for the project. And when you apply, you get, just by applying normal maps to a flat plane, you get something that looks like this, right? So this is a flat plane. I'm applying that normal map. You see the triangles, right? Just 2 triangles here. But with shading, it looks like I have a teapot extruding out of that plane, right? It's just a shading illusion, really. If you want to have the actual 3D deformation, you will need displacement maps. And with displacement maps and normal maps, you will get something that looks like this. I'm showing the grid here so you can see that geometric detail is actually there. With higher resolution tessellation, of course, you get a lot more detail. And if you don't want to render these triangle visualization, you can see the final surface like this. All right. Okay, so this is it. It's just the flat plane, right? Well, it's actually not the flat plane. I'm tessellating it. Let me remove the tessellation levels. Oh, that's not the right key. All right, let me remove the tessellation. Okay. All right, it's just 2 triangles now. And I still see the illusion of something here because we have normal maps. And if I'm going to apply displacement mapping, I will probably need a bit more resolution here. And then I can apply the displacement. So this is actually modifying the surface, right? It's not a very high resolution, nice tessellation. So if I want to get good details, I'll need to increase the tessellation level. And with that, I can get a much nicer looking surface like this. So this is actually using this tessellated surface. So the 3D surface and properly computing the shadows and everything. All right, so this is what we will be implementing for our upcoming project. All right, so this is where I'm going to stop, and you guys will be implementing that. And after that, with the upcoming lectures, I'll be talking about all sorts of different advanced topics related to interactive computer graphics. So I'll stop it here. Thank you all for joining another lecture for interactive computer graphics, and I'll see you all next time. All right. Bye.